Okay, seeing the time, I think I'd like to get things started. I'd like to welcome you all to the 2024 BIMR Summer Series. Before I introduce our speaker, I just want to make a couple of announcements. We have a couple of initiatives coming up organized by the BIMR. So there's an entrepreneurship symposium that's happening on March 7th that we'll be getting emails about over the next couple of weeks. I encourage you to sign up. It should be quite interesting. It'll just faster than how they take that set up. We also have our third installment of the Future Materials Innovators Program for graduate students. So we have graduate students who are interested in writing a proposal and getting funding for their own ideas. Please direct them toward that. With that, it gives me great pleasure to introduce our seminar speaker for this afternoon, Professor Nana Ofori Opoku from the Department of Material Science and Engineering. Professor Ofori Opoku got his bachelor's, master's, and PhD from Master University.
Don't hold it against me.
We think that's a pretty important awesome thing. Although he did go to McGill for part of that time, did his PhD work with Nick Trabatis, who moved to McGill when Rihanna was finishing his PhD work, but his PhD still for the master, so we have to give him for that expression. After his PhD, he did a short postdoc at McGill in 2014. And then took on a postdoctoral position at the National Institute of Standards and Technology, NIST, in the Netherlands, where he was until 2018, when he saw the light and he back to Canada to take a position at the Canadian Nuclear Labs in Chalk River. He was there until January of 2022, when we were fortunate enough to recruit him back to Master, where he has been ever since. He took on his position as assistant professor in the Department of Materials Science and Engineering. He's established a research program focused on computational materials science. And today he's going to be telling us about his work on microstructure and evolution models in materials science and engineering. So now yours.
Thank you, Alex. So first, I'd like to thank the Institute for giving me the invitation and Alex for making sure I kept my promise to deliver a talk. So today I'm going to try to give you an overview of some of the work I've been involved in over the past 6-7 years or so, and highlight, since I've been here, what kind of directions my research group is taking along some of those routes. So usually I like to start off by trying to give a big picture and situate at least my work and where I think that fits. And so in materials, usually what we're concerned with is at the macro scale, we're concerned with material properties and their behavior. My work tends to look at how we come to that understanding of that behavior. Specifically, my work tends to deal with how we develop physics-based models and then solving them computationally to arrive at microstructure that then determines those properties and that behavior. Okay. And so computational materials is a big field. And so further, I want to kind of sharpen that a little bit. So on one scale, we are in the kind of atomistic lattice type defects. On the other scale, we're really interested in kind of macro scale properties. I tend to find myself somewhere in here where I'm interested in things like interfaces, surfaces, microstructure, grain boundaries, and how those things emerge and how they evolve. Okay, so what is microstructure engineering? Well, let me first go back, and for some of those that may be a little young. So the Challenger disaster, short of it is, it was a polymer O-ring that was the problem. Okay. It was supposed to expand and keep gases in. It didn't, and let gases out. We have our catastrophe. My main point here is that it's a microstructure and it's a materials problem. quintessential Titanic. The problem here was the steel that they were using had a ductile to brittle transition temperature that was at room temperature instead of at lower temperatures, which caused the Titanic, the materials to fail. Okay? So I'm biased, obviously, so I'm going to treat everything as a materials problem. And so if you're not a materials engineer or a scientist, maybe this talk isn't the best talk for you. And then I like to show this because, again, I like to associate my work. And so is there a need for computational material science? I'm biased, so I'm going to say yes. If we take a look at the gamut across scales, where I may want to produce this part, I needed to have certain properties, but those properties actually start from here. So across those many length scales and time scales that these materials evolve, how are we going to actually figure out how they're evolving and what properties emerge? And it's not that I have anything against experimentalists, but sometimes in experiments, it's hard to see in situ or get some fundamental understanding as to what's going on at that level. And so computation then is a very viable approach in order to figure out some of those fundamental understanding of physics that drive these processes and these properties. Still on the idea of computation, and again, situating myself and my work, if I take a look at the many length and time scales from my previous plot, I find that it crosses not just many length scales, but also many time scales. And so what is the appropriate tool to apply? So similar to experimentalists, I'm not going to use the same apparatus or the same facility to do the same examination. If I'm interested in different things, I go where those tools are available, and I could do that. So at the very small length and time scales, we're interested in atomistic motion, lattice defects. We tend to look at DFT or molecular dynamics, density functional theory, or Monte Carlo. At the very large scale, where we're interested in things like heat transfer and mass transfer, we're perhaps looking at finite element analysis. And then in between, we need something to fill that gap. And so that's where I find myself with these mesoscale microstructure models as well. Okay. And particularly where I spent most of my career is in developing these called facial type models, which hopefully if you've taken nothing away from my presentation, hopefully you get an idea of what these sorts of models are about and what they could achieve. There's another class of models that I won't get into, but these are called amplitude models. And the idea of these models is they're supposed to encompass many orders of magnitude of both time and length scales. And this is somewhat coming from my physics tutelage in the sense that we want one model to do it all. So how do we get so many different length and time scales and the same set of PDEs, partial differential equations? So hopefully if I've situated myself and my work well enough, let me first acknowledge the people that have participated in the work that I'm going to present. And so this spans, like I said, many years. And so it spans from my work at McGill and at McMaster all the way to my latest stuff at CNL as well. And so the basic idea of my talk is I'm first going to discuss additive manufacturing, and specifically, is it really something new or do we already know what's going on, kind of thing. Then I'm going to get into, after you've solidified and you formed this material, the solid states of precipitation, and then if time permits and I don't drone on and on, I will hopefully also discuss a new approach, a new phase field approach that I think is missing some of the physics that are important for things like, say, nuclear microstructure or microstructure for nuclear applications. And so just to further beat the drum, what are some of the benefits of computation, at least in my mind? And you could agree to disagree with me here. So if materials properties depend on their underlying microstructure, a lot of what we know about materials properties is somewhat heuristic or somewhat empirical. And so can we kind of find some sort of fundamental foundation to underpin some of those theories? And so what simulations or computation could help us out in those areas is give us a bit of fundamental understanding. It could lead to better product design. Usually it's more cost effective if I count my number of cycles compared to, say, some of the apparatuses that experimentalists tend to purchase. And the ideal holy grail is that perhaps we could work together in some sort of synergy with experimentalists to kind of fine tune some of the directions that these experiments are going. So as a material scientist, this is kind of my bread and butter. The aluminum copper phase diagram, specifically, I'm looking at the aluminum rich side. And I show this because this is probably by far maybe the simplest or one of the simplest phase diagrams that I've come across for a binary system that is still rich in microstructure information. And so let's see the source of microstructure and what we need to know about what's going on in this phase diagram. So first, and for those of you that may not be familiar with phase diagrams, what I'm looking at here is I'm looking at what sort of phases are present if I combine aluminum copper as a function of temperature at fixed pressure. So if I happen to find myself in a temperature and a composition where I happen to be able to support two phases, I tend to form these nice dendritic-like patterns that we call in materials. In the high temperature liquid or high enough temperature liquid, you get these nuclei, they grow, and then they coalesce, and they form these sorts of nice microstructure patterns where each of those are different grain orientations. If I increase the composition of copper just a little bit, I tend to then get secondary phases that also form. And usually they're forming in the liquid or the interdendritic liquid that formed during the solidification process. If I decide to do something as a function of temperature, so I'm at high temperature first, I form a particular structure or a particular microstructure, then I drop that temperature to a little bit, I tend to form these very nice, either faceted or highly anisotropic solid phases within the solid I've already formed. So in all these things, the things that I'm considering as a theoretician is I'm thinking of things like, what's the crystallographic orientation? Do I need to concern myself with that? Surface energy, anisotropy, or elastic energy, anisotropy. Plasticity, am I concerned with that as the phases perhaps coarsen and move around? I'm always concerned with heat or mass transfer or any sort of mass transport process. Defects, multiple phases. And this might not be enough. If there's magnetism in there, what am I doing? Polarization, so on and so forth. So this is rich. And experimentalists tend to get a lot of this for free, but when you become a computational scientist, you need to concern yourself with some of these things. And so what tools do I need in order to tackle some of these problems? So let me remind you of this. And so I'm saying I'm going to be sitting somewhere around here because microstructure is what's important to me. And so let me discuss what phase field models are. So some time ago, I came up with these sets of slides because some of the presentations I was given, I kept getting asked, what exactly are phase field models? So I'm going to spend some time and hopefully get across what a phase field model is. So this is a quintessential problem. I have some phase beta that has nucleated or emerged from some matrix phase alpha. And I want to know two things: how this phase beta is going to grow and what's going to happen with the composition. It's a problem from like the 20s or 30s by a fellow named Zener. The conditions of my problem are the beta phase is at its equilibrium concentration, and then some far away, I have this average concentration C naught. This is the only equation I have. It drives mass transfer. But at the interface, I need to apply this boundary condition. But then I'm stuck because in order for me to know how fast this phase is growing and therefore how big it may get, I need to know where that interface is. But in order for me to know where that interface is, I need to apply this boundary condition. So which comes first? So we have found ways to solve this particular problem, but it's kind of like the chicken or egg, which comes, what do you need to do first? So at some point, we were smart enough when computers or sophisticated mathematics came along, like, well, in order for me to know where that interface is, I could track it. So I could track it, apply my boundary condition, move the interface, track it again, so on and so forth. Something like this is pretty simple if you have just one particle in a matrix. But if you have many, and if your microstructure is quite complicated, computationally, this is not a good thing to do. It takes too much effort, too much resources. And so this is where the idea of facial models come in. And the idea is, can I get the tracking of this interface for free while describing my bulk? So for a problem like dendritic solidification, where I have an extremely complicated microstructure, the tracking of such interfaces is not going to be ideal. And so then adaptive mesh techniques came along, and it turns out that you can track these interfaces as well, but still, if you have many of them, writing algorithms to do this is not trivial. And so can I write a model that will still get me this structure and the interface for free without having me to worry about exactly where that interface is? So facial models. So facial models start off being very toy, niche models that the physics community, particularly condensed matter, use to look at simple phase transitions. And then some people in materials got a hold of it, and we realized actually it's not that bad at examining microstructure as well. And so the idea of facial models is initially what you want to do is you want to identify the fields of interest that you care about in your system. So is it density? Is it concentration? Is it the phase? Is it the structure? Once you've identified this, you assume, at least at the microstructure level, that it's constant, except for where you have interfaces and surfaces. The next thing you do is you try to construct a free energy. We're all scientists. We can't violate certain laws. One of them is energy. And so you construct this free energy in such a way that you account for things like, am I having to go through a phase transition during this transformation? Do I need to worry about elasticity? Do I need to worry about surfaces? So once you do that, you construct this free energy functional with the caveat that whatever dynamics you choose to solve or kinetic equation you choose to solve this free energy is always minimizing energy or it's maximizing entropy. And so there, the dynamics, at least if you're a conserved variable, something like concentration or density, follows this Fickian type equation. And in this case, what I've constructed is the simplest facial model I can that describes Spinozzi composition or phase separation. I've identified essentially two equal wells with this quartic function. That gives me my two phase separated states. And then I've added in the surface term that separates those two separated phases. Then I run these dynamics, and I get microstructure patterns that look like this. So here what we're looking at is from left to right, increasing time. Presumably, I started off by quenching my system into this two-phase region where I started off with some unstable fluctuations, and then they separated it into one that it happens to be, let's call this A-rich, and another that is B-rich, for example. So that, in a nutshell, is a facial model. So now let's get into how we apply these facial models to microstructure evolution, and let's start with additive manufacturing. So additive manufacturing, for those of you that are aware, is a new manufacturing technique that uses powder, and it does it layer by layer. And so you lay down your powder on some substrate, you have some energy source, could be a laser, electron beam, you raster it, the powder melts, you add the next layer of powder, energy source, it melts, and you do this layer by layer. The idea of this manufacturing technique is it's supposed to be better in terms of its production of parts and their properties. So it's less wasteful. Conventionally, what we do is we cast or we make these big steel or metal parts, and then we machine them down. Additive manufacturing is supposed to get away from that, where you could program essentially the part you want to build through a CAD system, and then the machine essentially constructs it for you layer by layer and how you want it. It's similar to sintering, and so my somewhat facetious comment earlier is this actually a new technique or is it not? This particular manufacturing technique is rich with physics that conventionally in other solidification or casting processes, we tend not to contend with. So things like Maragonian convection, not that convection doesn't exist, but at the rate that conventional casting goes, convection is negligible in some of those. You're looking at things like recoil pressure, buoyancy and gravity, gas flow. And so it's physics rich, but I'm going to tell you now and spoil things that I'm not going to be encountering or considering most of these physics, at least at this first pass of what I'm going to talk about. The first pass of what I'm going to talk about is and if this is a new manufacturing technique, what sorts of microstructures do they produce and how does it compare with what we already know? And so to start off with, what we want to extract from a computational point of view is what the thermal history or what the thermal profile is like when you're doing one of these manufacturing processes. And so we go to someone who's very adept at finite element calculations, and they run these sorts of simulations, and then what we extract is the temperature profile. And what gets put in is things like what's the density of the material you're interested in, what the scanning velocity of the laser or electron beam is like, and what the power of that energy source is. So when we do, we could get a temperature profile that kind of looks like this. After the laser rasters, it melts a certain area. So you have a liquid, you have some two-phase region, and then you have the solid substrate that it's on. And so we take this information and then we input it into a phase field description. This is probably going to be one of my 3 or 4 slides, so let me try to break it down. What I have here is a generic phase field description that tracks the phase, i.e. the order or state of my system, and then concentration. The concentration term has a term that looks like a chemical potential, so the divergence of a flux, and the flux is related to a chemical potential U, and then some other term that tells me how fast the interface is moving and where I should apply certain conditions, in this case, concentration variable. The order parameter equation, i.e. the state, tells me things about surfaces and anisotropy. That's the first line. The second line here tells me about the driving force. In this case, the things I've extracted from my finite element calculations are things like the gradient, G, so the temperature gradient G, and the velocity V, and the M, C0, and K are all material parameters that are associated with the alloy I'm interested in and where in that phase space I am. The rest of the parameters you don't need to concern yourself with at this point. So when you run one of these simulations, for this cooling rate, so the cooling rate in this case is just the gradient times the velocity of what that interface is moving like. We get these sort of microstructural patterns. So these are called cellular fingers. What you see here is concentration. So blue is low concentration. The red is high concentration. And what we've measured here is the spacing from tip to tip. That's a characteristic measure of microstructure when you see these sorts of patterns. And then what we're going to try to compare it to this geometrical model that is somewhat well accepted in the literature in other casting and manufacturing where you can define solidification. Okay. So we find that at 2 different cooling rates, we get 2 different patterns that form, as well can be expected. The temperature is affecting how fast these things grow and what happens. And so we want to compare it to some experiments. So we found this in the literature that measured this spacing, this dendritic spacing, as a function of cooling rate with a similar alloy that we have. And then where our simulation fits is somewhere over here. Now, if I really squint, I can say, yeah, I'm not that bad if I kind of take a ruler and extend. But is that really the case? I'm off, but why am I off and what's going on in this particular description? I'm also missing a range of cooling rates as well. So how do I bridge that gap? So when I compare with these well-known solutions, I find that at least my current manufacturing technique that I try to simulate does not compare to these theories at all, which have been benchmarked or at least have been verified and validated against experiments. So my facetious comment at the beginning is additive manufacturing a new technique? I still don't have an answer, but I could at least say it does not conform to anything, at least in terms of this particular measurement, that we already know. The question could be asked then, how accurate are these theories that I'm comparing it to? Okay. We could also look at some of these things in 3D as well. And so the interesting thing about 3D, although we saw it in the 2D simulation as well, is you're leaving behind these rich pockets of liquid as this solid moves and consumes the liquid. Our assumption is that these rich pockets of liquid could potentially form secondary phases further down the line. So if you recall the phase diagram I showed you where I was saying if you change the composition and temperature in this phase diagram, you get different results. These little pockets could form some of these secondary phases that could be elastically different or surface or have high surface energy or those sorts of relationships. So in 3D, we find for somewhat of a similar cooling rate that our spacing is somewhat smaller than what it was in 2D. And again, our explanation here is that in 3D, you have other factors, particularly diffusion doesn't work the same way in 3D as it does in 2D. So in 2D, it's restrictive, in 3D, it's not. So in 3D, diffusion occurs in all directions, which tends to stunt then how these fingers emerge from the solid. In 3D, there's also theories, and most theories, at least with solidification, when you're worried about length scale, tells you that the length scale that results could always be assumed to be some sort of power law behavior between the length scales in your problem or in your system. In this case, the length scales are the diffusion length for both the concentration and the temperature, so the thermal length and the capillary length. Those are the only length scales we have. And then the different exponents, depending on the theory you have, adjust to fit that. So once again, we find that at least with our simulations, we're not conforming to any of these well-known or well-accepted theories that describe what we think we should be getting in terms of these dendritic patterns as well. We've also looked at things like how things are coalescing in this system as well. So we find that with increasing temperature, as you'd expect, you should have more liquid regions in your system. And how do you track that? And so we used Euler characteristic here to see essentially how connected our system is as a function of temperature. The idea of, as a function of temperature, what's going on with the liquid is we think that's where defects or secondary phases will tend to form if they're not closed. And some of these defects or secondary phases could be detrimental later on. And so if we know their distribution or where they are and the characteristics they have as a function of, say, composition, then we could feed that into other algorithms or into other theories to answer some very interesting questions as well. So that's the first bit about at least additive manufacturing. currently right now, what my group is doing here is we're trying to correct some of the missing physics that I did not account for at all in the first part. So in the first part, the only thing really I accounted for was just what's the temperature gradient? How fast is my interface moving once I have a solid? But there are other physics in there that matters, particularly when you talk to experimentalists that tell you, why don't you have simple fluid flow? That could be important at these extremely high temperatures. The interfaces are moving rather quickly. So what's going on? And so one of the things we're working on is including some fluid flow aspects and convection to see if we could truly ignore it or not. And additionally, does that bring some of the measurements that we made or some of our predictions about the spacing, does it bring it to conformity to these accepted theories that have been published already? So the second thing is still additive manufacturing related, and it's how does the direction you build affect the microstructure? So I said that is layer by layer. So if you want a particular part, I'm going to borrow this person's. So if you want a particular part, so I could build it layer by layer this way, or I could build it layer by layer this way. So that's the direction of the build. And that seems to have an effect on how the microstructure develops. So here is the first example. This was from an EBSE map from some colleagues. And what you see is you see more or less a very uniform microstructure. They're all kind of equiax. Here, you see a very heterogeneous microstructure. Some are very columnar, lenticular, and then you see some of these equiax regions. And it turns out that they both give you different mechanical properties. And so the question that we were asked was, can you let us know what exactly is going on, or can you give us some understanding as to why when I build it in these different directions, I'm getting different microstructures and therefore then these different properties. And so here as well, we had to do a finite element calculation to extract from the alloy of interest what the temperature history was like. For this particular experiment, or for this particular project, instead of just extracting just the temperature gradient across that melt pool, what we actually extracted was the full temperature history, the full temperature formulation and profile, so that we could put it directly into our phase field formulation. Okay. It turns that out for the two different directions, you also actually see different melt pool geometries as well, which is already suggestive of why then they would develop different microstructures. And so what we have here is we have a substrate or base metal that we assume is some polycrystalline microstructure already. And what we're doing is we're applying this temperature profile, the two different ones, and then we're seeing how this new single layer emerges. What we find is, depending on which direction we're in, we're getting first an epitaxial growth from the substrate, and then we're getting nucleation ahead of these fronts, some of these, and this in at least solidification, we call it the columnar to equiax transition, where you start off with these lenticular solids that grow, and then ahead of that solid, you get these localized nuclei of equiax grains. We also looked at, for example, what the concentration was doing while this process was occurring as well. And so what we find is, in terms of the concentration, it's not all that dissimilar from horizontal to vertical, even though we're seeing different nuclei that may occur for these different processes. We also looked at the effect of undercooling. So in solidification, what determines particularly for this columnar to equiax transition, those localized equiax grains that grow is how undercooled that liquid is ahead of that moving solid front. So not only are we seeing different epitaxial solid profiles that have formed, that then also informs the nuclei that form, because then the liquid ahead of that front has changed in terms of its temperature profile. And so at the end of the day, what we were looking at was, in terms of horizontal and vertical, because the two different directions see different undercooling ahead of that growing liquid, we then should expect that they should have different microstructures. And so the quick recap. So there we saw different behavior as a function of the growth direction, all dictated by undercooling, dictated by nucleation. And this, at least we think, is consistent with what they have also observed in experiments as well. Where we're going with this particular work is we're now examining more complex alloys, and we're considering multiple layers ahead of this growing front in terms of the powder layer that gets added. And I should speed up a bit. So this will likely be the last thing I discuss because I don't want to go too long. So solid clustering. So suppose I've run through these solidification experiments or simulations. I have my network of interconnected solids, but I'm a material scientist, and so I want to do some strengthening process. And so I take this material, I put it at another temperature, and I want to see what happens. That's where solid clustering and precipitation comes in. It's particularly very popular in aluminum alloys, although all other alloys can do it as well. And so you have this kind of single phase material, but it's polycrystalline. You quench it into this two-phase region, and then what tends to happen is it tends to form these precipitates that are supposed to strengthen the material. The idea here is the more obstacles you have in this material to defect motion, the stronger the material is. And so here, for this particular problem, I contend that the things that I was discussing earlier that I was kind of wash away are going to be somewhat important. And so how do I bring that into a modeling formalism? So phase field is what I've been talking about, where we're looking at these very uniform fields. The only defects we really have are surfaces, grain boundaries. But if we go back to somewhat of an atomistic representation, and I look at how from atom to atom these periodic structures are arranged, it turns out that I could get a lot of rich physics by treating my order parameter as a periodic field. Just as an example, if I'm treating my order parameter as a periodic field that has an equilibrium wavelength, if I happen to change that wavelength, Hooke's law tells me that it should come back. And so rather than thereby describing my system by a periodic field, I've inherently have introduced elasticity, or at least zeroth or first order elasticity. And so one of my previous slides, I wrote an equation that was similar to this, and I said that was the simplest model you could come up with for a facial model, and I used it for the Spinol decomposition. It turns out that if I change the behavior of this particular kernel, so before it was just a surface term and a constant term, so it was this, a surface term and a constant term. If I do some kind of pseudo-stability analysis, I could find out for my phase field, the only kind of stable wavelengths are at the long wavelength limit. If I change this particular kernel and I happen to add an additional surface contribution, it turns out that I move that stability to somewhere where I could stabilize different structures. So I didn't develop this. This goes back to Swift and Hohenberg back in the 70s. And they used it to look at convection instabilities. And so what you have is you have like a liquid, you heat underneath it, and then you form patterns that look like this. Someone came along, Ken Elder, back in the early 20s and said, actually, if you go from solving this model that they use like this, which is just minimizing energy, and you assume that what you have here is a conserved field, and so you apply some sort of Fickian equation to it, you get patterns that are very reminiscent of crystal structures, so repeating structures. And so effectively, I've gone from something that looks like this to something that looks like this. I've gone from this kind of spinodal state to something that is highly regular and repeating. And so it's this sort of model using periodic structures that I'm going to use to examine solid clustering and precipitation. It turns out that this particular model could also be motivated from a more fundamental theory, in this case, classical density functional theory. I won't get into that, but when you do and you construct a full free energy functional that includes composition, density, you get a set of parameters that all modulate something physical. So I get something that modulates peak heights, temperature. So essentially those periodic peaks, I could think of them as pseudo-atomic positions. And so modulating those peak heights are like modulating temperature. I get things that could fit to some bulk, phase, or energy description. I get a bunch of terms that link to elasticity, surfaces. And I get terms that tell me about the structures that I should or that I aim to create with this method. And I get things that tell me about solid interactions between two things, two different elements. Okay. Because I have a free energy, I could play my trained thermodynamic game and try to recreate what sorts of phase diagrams, i.e. equilibrium states, that exist with this free energy. I should mention that all of these are toys, but they are very reminiscent of phase diagrams we've all seen before. Iron carbon, copper nickel, or any sort of eutectic phase diagram. Okay. So let's recall this is really what I'm after. I'm trying to find some fundamental understanding as to what really happens, what's mediating this precipitation or clustering. And so I'm going to create a facsimile of the actual copper, aluminum copper phase diagram. And I say facsimile because no one as yet over the course of this particular treatment of phase field crystal models has developed a very quantitative way to map thermodynamics to this particular formulation. And so it's somewhat facsimile where we've tried to get the right two-phase coexistence, the right solubility, right kind of homologous temperature, and things of that nature. Okay? So what I'm going to do is I'm going to take some material, and my assumption here is that defects, particularly dislocations, are what will mediate this transformation. I'm going to quench it into this one-phase region where I expect to get this polycrystalline network. And then I'm going to quench it yet again to this two-phase region where I expect the clustering to occur, picking up some of this secondary phase information as well. And so this is my result. So the initial thing you see is my highly dislocated solid. So what you're seeing here is you're seeing the concentration profile overlaid on the atomic positions. Blue is low concentration, in this case, of copper. Red is high concentration of copper. So if I take that highly dislocated or that highly kind of liquid-like structure and I just quench it to this one phase or one phase region at 1 or 4, my structure completely heals. So I just get a single phase back. If I quench it to this 2-phase region, all of a sudden these dislocations start mediating clustering. They start attracting solute. If I change the composition of my alloy, I get a different, still clustering, but I'm getting larger clusters, larger precipitates, if you want to think of it that way. So what's going on here? Well, first, let's take a look at exactly what the dislocations are doing. So what you see here is you're seeing dislocations. So the curves are dislocations that are on the surface and the crosses are in the plane. As the system evolves, what you're seeing is the dislocations move around, the solute is attracted, and then it turns out that everywhere you see one of these clusters or solutes, it's dressed by dislocations. Okay? So dislocations are what are mediating this process. So we could actually put some math to that as well. So my apologies. So what we do is we go to our work of formation, or we go to nucleation statistics. So usually what we're concerned with, at least when you teach undergrad, is you care about the bulk, you care about the surface, but it turns out that you could also account for strain, dislocation energy, and you could also talk about solute interactions as well. So if you develop such a model, and here, this term here is a measure of my dislocation, so it's the Burger's vector. So if I take a look at what the work of formation looks like as a function of how many dislocations, i.e. the Burger's vector, I find that with just say a single dislocation, I have an energy barrier associated with my transformation. But as I add more and more dislocations, my energy barrier effectively disappears. So it seems like dislocations are removing, or defects are removing, the barrier for nucleation of these precipitates. You could also track what the radius of this precipitate is doing as well. And you find that, yes, you do recover like a critical radius that's also associated with this transformation as well. You could also take a look at the strain map. So where are the dislocations and concentration? What are they doing? Because if I'm saying that dislocations are mediating, dislocation tends to distort lattices and introduce strain. But then you could also do a simple free energy analysis as well, where in the one case, so in the dotted line is where I'm assuming that my solid is strain free. And then I've introduced a strain parameter. And again, my double well that had this energy barrier slowly as a function of strain is becoming a single well. I.e., again, I'm removing the barrier associated with that transformation. When we first did this, a reviewer had said, how do you know that you're not violating energy? And so we also made sure that we tracked the total energy in the system as well. So while locally, in this case, while locally the energy might be rising, overall in our system, we are maintaining, minimizing energy as well. Okay. We could also play this game with ternary alloys as well. And the one thing that I want to point out in ternary alloys is interesting. So if I take an aluminum copper alloy and I take an aluminum copper and magnesium alloy, it turns out that just by adding that additional alloy element, I get different solute behavior or different clustering behavior and statistics as well. And so can we explain what's going on here with the addition of a secondary alloying element? And here our explanation was that we're actually going through a two-stage process. So initially, when our structure is highly distorted, almost liquid-like, both solutes tend to be attracted to the dislocations. But then once the critical radius is reached, one of the solute components, after having stabilized that initial cluster, actually decides to leave because it's no longer the equilibrium or the preferred place for it. And then we could look at also the work of formation associated with this as well, and the critical radius calculation for this as well. We've also, and I say we, but definitely not me, no one lets me near experimental apparatuses, but we've also validated this with experimental observations as well here at McMaster, where we've looked at an experiment looking at clusters early on, then 15 days to see if we could recover essentially the growth modes that are associated, specifically the anisotropy associated with growing this cluster in this particular direction. Okay, and when you do a high resolution SEM, you find that essentially the wisps that are around these clusters are also dislocations. Okay, so I will stop there because I think I've talked more than enough. Thank you for your attention. I will be happy to answer any questions or comments you have.
I assume you could build, like, you could add, like, chemical reactions.
You can. Yeah. So there you would go into the reaction diffusion type equations and figure out how they couple to the equations that I'm already looking at. How about you buy me dinner?
This kind of model, does it apply to block polymers? Like, I know that you're using hard materials, but I think of the soft material, right?
I actually have, so I had a summer student, and I actually currently just have another undergraduate student. I saw Kyla walk in. So Kyla was nice enough because I had an undergraduate student come to me and go, oh, the computational model is interesting, but I'm interested in biomaterials. I stayed away from biomaterials, and so I asked Kyla, and she gave me a tutorial on what's important or what's going on, and block copolymers were one of the things. And so using at least one of the first models, the Cahn-Hiller model that I showed, you can actually write down a set of equations that can look at block copolymers as well and how those microstructures form. There, at least where I'm somewhat ignorant of is what the driving forces are, because I know you have the ideal term, but then what are the interaction terms like that will drive those sorts of formations? So that's what I have the student trying to find out. So arguably the clustering stuff I presented is solid state precipitation. So I haven't done extensive work in terms of, if you're interested in steels, I assume probably austenite to ferrite or, okay. So there are facial models that have been developed to look at that as well. So if you're interested, we could talk and I could point you in the right direction. It's a Fourier transform. So we take the Fourier transform and then we square it. And then that gives us a structure factor, which then we could extract the length scale. Yeah. We could also do the very materials thing and take a ruler and draw, because it's regular enough that we could do that. So I want to say yes, but I don't know enough about that system to say yes. But the idea usually with these facial type formulations is, as long as you could tell me the thermodynamics involved, because that's really where it's important to define that driving force, and the rest I could do for you.
nearly huge cooling rate, correct?
Yes.
And this is great. I have two interrelated questions. First, how to achieve such a cooling rate? And secondly, and most importantly, how to measure?
How to measure, I'm not entirely sure on. But in terms of how to achieve it, so just in additive manufacturing, due to the power of the lasers, that is the cooling rates that they tend to achieve. And so you could put sensors and try to measure.
It's not approximately 10 power 5. It is 3 multiplied. Therefore, as if it's an accurate value. How can it be?
Well, it's an accurate value because someone ran this simulation for me and told me what the temperature gradient in their simulation was. And so that's what I used.
And we still need to understand one thing. Slide number
Yes.
What is lambda,
Oh, lambda is the dendrite spacing.
which is measured in meters? Yeah, good. Length, meters, length, meters, length, meters. You have this product. Does it mean that m plus n plus s must be equal to 1?
Yes.
Why? Oh, no, no. Yes. Good. And finally, acidic question. Slide number 4.
You're not allowed to ask silly questions, Dimitri.
But in this formula, I didn't find KMI.
Oh, that is true. Sorry. So these particular parameters are buried in this effective constant here, or not constant, function there, CF. Yeah, they are somewhere in this formulation. So I had removed the slide that talked more about this, but I thought it'd be too much.
Right. That, I think we can thank Donna one more time for being so.
Thank you.